All right, hello everyone. Thank you for coming. My name is Igor. I work for WhatsApp and an engineer there. And today I'm going to be talking about us moving our users across data centers. So for the last few years, WhatsApp was in the progress of migrating or integrating with Facebook infra. During this time, a lot of stuff has been changed. To name a few things, we moved from FreeBSD to Linux. Instead of using R16, we're using R21 now. We used to use bare metal machines. Now we use more and more containers. Instead of manual production operations, we're switching to automation these days. And instead of having a local storage that is hosted on our backend machines, we're now moving to hosted DB services. And this talk will be focused on the last piece here. Before we move on, it might be worth mentioning on a really high level how WhatsApp architecture looks like. So what happened? OK. If we would try to trace a message that one client tries to send it to another one, then on a really high level, the way it would look like is that that phone would connect to our front-end servers that we call chatd, which are stateless machines. These machines would fan out and try to figure out all the data that they need by calling to our backend machines that store data. Mostly, they used to be storing the data in amnesia. Then once the data is there, then the message was routed or is routed to another chatd machine that is connected to another phone. And then the message is being sent to the receiver. So let's talk about the backends. We have many of them, more than 20 of the backends. All of them store some kind of data. We tend to split this type of data into three different types. Relationship data, which stores kind of relationship between different types of entities, like what are the groups that I have, what are the people that I block, things like that. Then it's a key value information, like what is the platform of the device that the user is using, or what is my profile picture. And then there's some miscellaneous data. The big example of that thing is the public encryption key storage. These keys are used for our E2E message encryption. So all of these backends are stateful. Most of them, 95% of them, used to use amnesia before. Some of them used some custom file system-based storage. Here we will be focusing mostly on those that were in amnesia. We also used to have a single data center. We used to copy our stuff to another warm data center, but we never actually had to move our traffic to that one, and we never tried it. So why did we decide to migrate? Big reason there was to start leveraging internal Facebook systems more and more to take advantage of them. We wanted to start using Facebook's deployment techniques, testing, monitoring, automation, all this stuff. And once we would be there, the idea was that it would be so much simpler and easier to share knowledge and technology between two orgs. Another big, more technical reasons why to move was to move to actual real hot multi-data center architecture. Moving a little bit forward, the ways that the systems that allowed us to move to the hot multi-data center architecture were partially, some of them are part of Facebook, some of them were built in-house. So one of the notable examples of a system that was built in-house is Forgets, or drop-in amnesia replacement that Mihail talked about last year in Sweden. And there are two data storages in Facebook that also provide similar properties. One of them is Tau that exposes its API as a graph, vertices and edges. And you could check its architecture. It was presented 5 years ago in Data at Scale. And ZPDB, which is the distributed key value store, which was also mentioned in Data Scale conference before. All right, so how did we decide that we would like to migrate our data? First of all, the idea was that phones would still connect to WhatsApp data centers, would still have our warm data center replication. But then once we are there in the WhatsApp, we would start replicating our data to Facebook. Of course, because of our terms of service and legal restrictions, all the data within Facebook had to be encrypted so that only us would be able to access it. And then because the data store where we replicated the data has replication within Facebook by itself, that data will be replicated later within Facebook itself. So once all the data was there, the next step was to start moving users to Facebook so that the Facebook data would be used as a single source of truth for everything that these users do. However, we wanted to make sure that if something is wrong on that side, once we moved users, we wanted to be able to switch users back to WhatsApp, to the all well-known stack, right? So in order to do that, we had to figure out how to replicate data back to the old data center for those users who are switched to Facebook. Once we are fully aware that everything on the other side is working great, we would be able to cut the replication traffic and turn off WhatsApp data centers. All right, that was the plan. And once we figured it out, there was a time to start executing on it. The very first problem that we had to face was to figure out how to talk to Facebook systems in general. The thing is, in Facebook, Erlang is not a language of choice. It's not a first-class citizen there. All the systems, all the clients for most of the systems there are built for Python, C++, or Hack. Erlang is not there, so we had to figure out how to talk to those. The language that we decided to choose was C++. Because of obvious choice, Beam is C also. And we tried to do that architecture first. We still planned to have an Erlang backend in WhatsApp, and then we actually didn't really plan, that's what we did. We installed an Erlang gateway machine inside Facebook. We collocated a C++ gateway machine on the same host. And that C++ gateway machine knew how to talk to the remote DB directly. That's what we did at first. We tried several approaches how to actually make this communication between Erlang gateway and C++ gateway machines. Many of them worked. However, when we started to do load testing, all of them showed that there are issues. And although things worked, in the very end, we understood that there are two main issues with that approach. The very first issue is that the Erlang machine that we have on Facebook doesn't really do anything. It just gets a message and passes it to C++. However, we need to spend energy and time tuning that machine. And because it is collocated with C++, sometimes it's really hard to figure out what's going on. Why the beam is slow? Is it because of C++ taking all the resources, or because there is some inefficiency within our code itself? So we decided to drop this approach and instead learn how to talk to C++ directly across data center. And that really worked. It really helped us because there was no two processes to tune on a single machine. We only had to worry about C++ only. There was no Erlang node that didn't do anything but message passing, which is just work CPU wasted. However, of course, the technology stack became more complex because we had to learn Erlang how to communicate to C++ across data center. We had to build a custom TCP-based protocol to do that. That protocol, because of the restrictions on the firewall for Facebook that did not allow us from outside to connect to anything within Facebook, had to have two modes, which is listen mode that would listen for Facebook machines to connect to Erlang, and the connect mode for those machines that are already deployed within Facebook itself. On top of that, we had to build a load balancer that would choose to what gateway machine to route requests to. A really great algorithm that helped us to achieve it in a really short time frame was a power of 2 algorithm, which you can Google. It's a great paper from a long time ago. It works. And because Thrift is the serialization protocol of choice within Facebook itself. We were looking longer term and where we would not need the C++ gateway anymore in the future, so we had to implement the Thrift serialization protocol within Erlang itself. In Thrift, you do code gen, and the way we did code gen by generating records. Records are not really great with hot code loading, so we had to spend some time figuring out how to generically solve that problem there. All right, once the Erlang C++ communication problem was solved, it was time to actually start copying the data. Before I will start talking about this, it is worth mentioning one of the components that we have in Facebook, in WhatsApp. We call it Gen Factory. What is Gen Factory? It is a group of Gen servers that are split into two different groups. One is dispatcher, that gets work or request and figures out which worker this request should be executed on. The Gen Factory were presented by Rick Reed in Erlang Factory San Francisco 4 years ago. If you'd like to read more or know more about this component, feel free to check the talk. It is great. However, for today's scope, it is worth mentioning that we have 3 different routing schemes within Gen Factory. One is consistent hashing, which means we would get a key and calculate the hash of that key, and that hash would tell us which worker should execute the request. Great thing about that mode is the write serialization, right? You guarantee that there are no 2 workers that are working on the same key at the same time. However, the head-of-line blocking is true here. If there is a key that is really long, all other keys that will hash to the same worker will have to wait for that key. In order to solve that problem, we have another mode, which is called cure. What cure does, instead of trying to hash the key, it would just check for a given request what is the first free worker that can take work, and that request would be sent to that process. It's great for head-of-line blocking. However, if you need to make sure that no 2 requests are executed at the same time for the same key, cure doesn't really work. So to solve that problem, we have a mix of the first 2, which we call sticky cure. The way it works is like that. For a given key, it would check if there's a worker that executes a request for that key at this moment. If there is one, then we'll choose the same worker to do the next request. If not, then we'll choose the first free worker and send a request to it. And it worked great for us. All right. We know what Gen Factory is. Now, we need to know how our backend looks like inside, internally. So the way it works is there is a Gen Factory that gets requests from outside. Once it got a request and validated the request, it executes some business logic, and that business logic talks to Amnesia, which is local on the same node. When we started the migration, we set this goal for us. We want to keep the business logic the same. We didn't want to change the business logic of every backend to move to the different data center. We only wanted to change the data access layer, which makes sense, right? We only want to change one thing at a time. However, if you look at this diagram, you see that there is no data access layer right now. So the first step for us to go towards the migration was to extract this logic. We did this by introducing a module type, which we call DB module. And we said that now business logic doesn't talk to Amnesia directly anymore. It calls into DB module. DB module knows how to transform the business request to Amnesia specific request. Once this was done, we were able to add another component in the middle, which we call DB switch. What DB switch did, it called into local DB module first, once receiving a request from business logic, made sure that the request inside Amnesia executed correctly, and then after that, it called into the remote DB module that knew how to do exactly the same request for the remote DB, which was in Facebook. Now the problem is our remote DB was in a separate data center that was in a separate owned by a separate company. In order for us to talk to that data center, we had to go through public network, which is total crap, as we all know, right? So doing 2 calls is not really a great choice because the remote network would affect our online traffic if it was slow, right? And it was slow most of the time. In order to solve this problem, we introduced another component in the middle, which we called dbcure. It was a Gen factory running sticky queue mode. And instead of calling to the DB module directly, we casted a message to the dbcure. Then dbcure itself, once it had time to process the next request, it called into the remote DB module, and that called into remote DB. All right, awesome. Now we have a pipeline to copy our data. We're done, right? Not really. Because the public network is bad, errors happen, right? And we need to make sure that we know how to handle those errors automatically. The way we did this was by introducing another component that we called DB replay. It was a log. Every time we had an error, we added a message to that log. Inside that log, we had a loop that would check if there is anything new in that log that would send a repair message to Gen factory. Now, what is actually a repair message? How do we do repair? The very first idea was to store all the operations that actually failed into the DB replay log. But once you do that and you have a lot of errors, you have a lot of data to store, right? In addition, we also already had a component within WhatsApp that did something like that. And we knew how hard is it to store all the operations and make sure you can replay those operations on errors and things like that. So we decided to do something simpler. And instead of storing all the operations that failed, we just stored all the keys that failed. So once we had an error, we stored the fact that that key has failed to replicate to remote DB. So if you do that, how your remote repair operation looks like. The way we did this was by reading the whole local data for the DB and storing it on a remote DB. Basically rewriting everything that you have for remote DB for the local DB remotely, right? What's great about this approach is that the repair operations become idempotent, right? You can retry them again and again and again. It doesn't really matter how many times you retry them. They always set the correct state to the remote DB. It doesn't really also matter if there is organic traffic for the same key coming. Once you repair the key, again, we force the correct state on the other side. All right, now we have a way to deal with errors. What's next? The thing is, sometimes the network is bad and we have network cuts, right? Sometimes errors are just, there are too many of those, too many errors. What do we do with that? The problem is that if you have too many errors, you start hitting remote DB more and more with the loop that we just described, right? So the things become worse and worse as you try to repair the errors that are happening right now. And you can't really go out of this loop because you're just making things worse. To solve this problem, we introduced this concept of feedback. So now instead of sending just errors to the DB replay, we send everything, results of all remote operations, whether it was OK or error. And then before doing a repair, we checked, OK, what is the current feedback success rate? If it's more than a good amount of percents, then we say, OK, it's fine. We can repair the key. If not, it's probably OK, it's better to wait for now because something is not right. Remote DB is not accessible. All right, it's great. However, imagine that we had a network cut for a few hours, right? And now everything is good again, and it's time to repair all the keys that we accumulated for this time. Yeah, it's great. We do that as fast as possible, and now we kill our organic traffic because of that, right? How do we solve this problem? In order to solve this, we introduced a rate limiting configuration, right? So before doing the repair, we said, okay, what is the current repair rate that we have in our system? If it's good enough, it's slow enough, then yeah, it's fine to repair the key. If not, let's probably wait a little bit more. All right, now imagine we do all this, and there is one key that is really hot. It's being retried again and again and again and again. Million times per second, we get the same key being retried organically, and it gets error again and again, and we put it in the log again and again, and we retry it, and it's again a never-ending loop. How do we solve this problem? We did this by introducing another concept that is checking if the current key is currently in flight, right? Before actually trying to repair the key, we would put it into a hash table that would say, okay, I'm currently trying to repair this key, right? Every time we get the feedback for that key, we would remove it from the hash table. If we get the same key and it's in flight, we don't really need to do anything with that key, right? Because it's in flight. We already tried to repair it, so we can just easily skip it and move on. All right, it looks great. But what if the same key is being retried again and again and again and again? Yes, we check for in flight, but our repairs are pretty fast, right? We can do like a repair in maybe 20 milliseconds or something like that. Is it worth retrying it again and again and again? Well, not really. We should probably back off, right? Every time we repair a key again and again and again, and after each error, we do check if we should back off, and we would do an exponential backoff, right? If it's really worth waiting a little bit, maybe a minute, 5 minutes, we would say, okay, let's wait a little bit. If not, okay, let's repair. Okay, all good. What if after all this, the key still cannot be repaired, right? Something went really wrong, the pipeline had a bug, and the key is just, we can't repair it. Something is not right. Well, we should stop at some point, right? We did that by introducing a persistent error concept. Every time we decided that it's time to retry a key, we checked how many times we did retry so far. If we retried for a day, for example, right, probably something is not right, and it's time to look at the key and figure out what's wrong with it, right? So we put this into this log that we called p-error log. In that case, the person would be able to look at the key and figure out like what's wrong with the system, try to debug the things. And once they were ready and were sure that things went fine now, they were able to flush the keys that were, permanent errors before into the replay log, and everything would continue from the beginning for those keys. All right, we have a great loop that checks for errors and knows how to try them and stuff like that. But what if we crash and we lose a disk, right? There's no log anymore, and we have all these errors that accumulated that will never be fixed anymore. And we actually had this in our production. In order to solve this, we had to start replicating this log. We chose a node for each node that does a replication. We chose a peer node and replicate everything that we put into the replay log in a peer node. Now, the question is, how do we fix the problem when we detect that we start without a disk and that had to be there? The easiest that we came up with was to just ask the peer node to flush the last n minutes of everything that was put into the log back into the log on the node that we're just starting right now. Remember, because the repair operation is idempotent, it's fine to repair the key that has already been repaired before. So it probably should be fine to replay more than you actually need, but it solved the problem, right? Okay. Before we're moving forward, I need to tell you about one of the properties about Genfactory. So what if a Genfactory gets too many messages and it can't process them fast enough? The way we solve this problem is by saying, okay, if the message queue is too large, then we probably should discard, okay? What if dbqueuer discards? The problem is that if dbqueuer discards, then we will never do a remote call for the key. right? If we never do a remote call for the key, we will never send a feedback to the DB replay loop. We'll never know that the key has never been replicated to the other side. The way we solve this is by introducing a DB dirty keys adds table. It worked like this. So before doing anything with the key, with the operation, we first would insert that key into that adds table. After that is done, we called into local module, we called into remote module, we did a feedback loop, and once it is done, we deleted the key from the DB dirty keys. Inside DB dirty keys, we had a loop that checked how old are the keys that are there in the table. If the key is too old, maybe 5 minutes or so, then probably something is wrong with it. Probably we discarded or lost track of it. Let's repair it. Let's flush this key to the DB replay loop, and it will be repaired automatically. All right, but what if a node crashes? This is an in-memory state. Do we need to replicate the state also? Well, maybe not. If the node crashes, then, well, we're fine with that. But we probably should be able to somehow fix the lost keys that were in flight when the node just crashed without losing the disk. The way we did this is by introducing DB dirty log module. Every time we inserted a key into the adds table, we also wrote it into the log. When a node starts and it sees that there is this log file, it flushed last 5 minutes of the keys that were added there to the DB replay. Make sense? Again, the same properties apply because the operation is idempotent. It's fine to repair what has been repaired already. Cool. So with all this logic, we now have data on the other side. However, the issue is that the data that we have on the other side is only the one that has been accessed with organic traffic, right? What about the data that is not accessed? What if there are people who weren't using WhatsApp for quite some time? How do we deal with that data? In order to solve this one, we introduced a module that we call dbcure that, actually, wait, it's not what I'm talking about. OK. All right. Once it's on the other side, the next step is actually to validate that the data that you have on the other side is valid, right? It's not just enough to copy the data. You need to make sure that the data is exactly the same as that you have on locally right now in order to make sure that it's OK to switch users to the other side. The way we do this is by introducing a comparison step inside the dbcure. So once dbcure called remote module, it removed the key from dirty keys, it checked if the result of the local operation and the result of remote operation is the same, right? If it's the same, then all is good. We're OK. If not, probably we should try to check what's going on. The issue with that is that the compares can be flaky. The compares can race with organic traffic. The compares can race with repair loop that is currently being in process. And we don't really want to look at all this flakiness all the time. How do we deal with this? Well, we probably need to retry. We did that by introducing a dbcompare adds table again that would have all the keys that failed initial compares, right? Inside the dbcompare, we had a loop that checked if it's time to compare the key again. If the key is the same now, then we're OK. If not, let's compare again. Well, the same issue applies here. What if the key is not being the same for a very long time, right? What if it's been a day and the key is still not the same? Probably worth putting it into the same persistent error log that we talked about before. So if the key is not the same, we check if it's been a day. If it's been a day, yeah, it's probably not worth retrying it again. And we'll put it in the log, look at it, and figure out what to do next. All right, we copied all the data. The data is valid. But let's talk about the offline data, or the data that is not being touched by organic traffic that I talked before, right? We did figure out how to copy offline data, the data that is not touched by organic traffic, by introducing this DB crawler thing. So the DB crawler would crawl the local DB and just put all the keys in the DB replay loop. That's it, right? By doing that, you get all the goodies of rate limiting, in-flight keys, errors, and all that stuff just for free, and you're done. You have only offline data on the other side. However, it's probably worth to actually also compare this offline data, right? We don't have this here. Let's introduce another mode to the DB crawler. Every time it crawls a key, it checks what is the current mode. If it's repair or migrate, then we put the key in the DB replay loop. If not, if it's compare, then we just put it in the DB compare, and again, the existing loop will figure out what to do next with the key. Awesome. So now we know how to copy the data, and that is how we did it. Really simple, right? OK, cool. So now the data on the other side, it's both offline and online data. We know that it's correct. We validated all of it. Now, how to move the users to the other side? We try to figure out how to deal with it, how to make sure that the data is writable, and we actually move the traffic. However, it's really hard because our replication is actually asynchronous. When you switch the traffic to the other side, like it will race, right? You will start using the data that is stale. And your writes on the other side can be overwritten by the replication stream that hasn't arrived to Facebook yet, right? Makes sense? So the way we solve this is by actually saying that the key that we're currently trying to move will be read-only for some time. We said that we need to make sure that if a key is read-only, an app is still useful for that key. It can't change its profile picture or status, but it's fine. It still can't send messages, right? The way we did this is country by country, or a phone number prefix, if you say, right? We took a single country. We made that country read-only for that particular backend that we're currently trying to move. The next step was to accelerate the DB replay repairs. So there is something in DB replay loop right now happening while the key is read-only. And we said, OK, let's not check for backoffs. Let's not check for rate limiting. Let's just do the replace as fast as possible right now. There might be that some keys were still persistent. Let's put them in the prior log. Let's put them aside for now. Once that is done, there is no replication stream going to the other side anymore, and it's safe to switch traffic, right? So that was the next step. We moved the traffic to the new data center for that country. Once this was done, it was fine to enable writes for these keys. However, if the key was persistent error, then probably there's something not right for those keys. It's probably not safe to enable writes for those. Let's keep them read-only for now and look at them manually and figure out what to do with them. Fortunately, we didn't even had ever a persistent key during the move, so we didn't have to do that like ever. Right, the whole process was pretty fast, less than 5 minutes, considerably faster than 5 minutes in practice. In theory, it never had to last more than that. Cool, so now we have users on the other side. Now we need to figure out how to replicate data for those users back to the old data center, right? Because we want to make sure that we can move users back if something is wrong. And great thing about that is that we can do this by just changing the configuration. Remember, we had a local DB module and remote DB module. So now the previous local DB module that used to be local for us in the previous data center is our remote, right? The previous remote module is our local now. Yes, we need to teach DB crawler how to crawl the DB, the new DB, because it's different. But everything else is exactly the same. We don't need to change any code. It's just a configuration change, and it works. And that's how we moved our users to the other side. What did we learn during the process? Data migration turned out to be super very hard. Yeah, the ability to validate the data is crucial when you do the data migration. We found so many issues just by doing comparisons. We need to think about possible failure domains before we actually start moving the data to the other side or copying it. However, it's not worth thinking about them too much. Yes, there will be something that is obvious, but let's not overthink anything. Because wherever you do, there will be unexpected issues. They will happen for sure. and you should be ready to tackle them. Fix them, make sure everything works, rinse, and repeat. I mentioned several things, several topics during this talk: Forget, Tau, ZPDB, and Gen Factory. All of them were covered in the previous conferences. These are the names of the talks and links to those talks. This presentation is actually available in the app, so the links are ready to be clicked. Yeah, thank you.
All right, we have some time for some questions. Oh, sorry, I'll get this one first.
So you mentioned a lot of elements in your feedback loop that was to correct small issues that would be popping up all the time. And I'm curious, did you find many of these issues in development and analysis phase, or it was just like all live and figuring out as you were having trouble migrating it for real?
Yeah, it was the later. Yeah.
Thank you. Just a quick technical question. How did you keep track of the keys in flight? What was that system? Was that like a database? Was that in memory? How did you expire those keys and so on?
It was just a nets table.
Okay.
Yeah.
Was that like a separate service, or was that just in memory
Just
on
a
one
separate
node?
table.
Okay.
Yeah, just a nets table, that's it. As easy as it is.
Seems that you faced so many problems. How long took to cross this whole thing, the whole migration?
Multiple years. But the good news is that we're done.
All right, any more? Oh, here it is.
So it looks something like AMQP, like the way you managed, lost messages. Would you do anything differently today? Would you use a ready solution like Rabbit? Or?
Well, the thing is, all this stuff came to us during the migration, right? So it wasn't worth like trying the third-party library just out of the blue because it's there. And also the tight coupling with the backend internals that we have like also affected the choice here. Third-party library is great, but you will need to tune it anyway. And you need some time to figure out how it works with your existing system, right?
More questions? This side of the room really needs to step up. That side of the room like asked 3 questions. Come on, somebody's got to grab a question. All right. Oh, we got one.
So you mentioned when you were tracking bad keys, and then later on you said you added the good keys as well to that, right?
Not really, no.
Not really. Okay, I misheard you then, because
No,
it sounded like
yeah.
later on. Okay.
So we had this feedback stream, right, where we said if the key succeeded to be copied, if the copy replication succeeded or not. If it wasn't a success, then we would write it in the log. But if it is a success, we would just increment the counter and move on.
Gotcha. Thank you.
Okay, now you guys are running me around the room here. So.
Did you have big differences, like in the WhatsApp system, you're storing in a certain type of database. Now you're moving over to these Facebook-hosted databases. The quality of the database or the trade-offs maybe changed, or was it pretty much a one-to-one mapping in terms of the kind of database you had that you were using before and after?
Right. We used to use Mnesia. The great thing about Mnesia is all the data is in memory, right? Which means it takes microseconds to access the data, no errors, nothing. Now it's a hosted DB, which goes through a network, which is a private network, but it is still a network, right? Which is slower. So yeah, there is a difference, but overall, on a high level, hopefully you didn't notice anything, right? So it's great, works.
All right.
Hi.
Hi.
So my question is, how big was the team? And also because it took multiple years, presumably some people left, some people came on. So how did you sort of like onboard new people? What's your documentation? Because it's really complicated.
There was documentation. There was knowledge transfer. offline month to year, I guess. Yeah, it was a bad one. Good news about the migration here was that we had different backends to migrate, right? So there was a common framework, but then each backend was an individual piece of software that had to be integrated with it and moved to the other side. So different people were able to work fairly independently on each piece of their backend here. So as new people arrived, we were just onboarding them on the backend itself and like high level of the framework. Did I answer your question?
Yeah, how many people were there?
Oh, how many people? At first it was 2 of us. Then it went into like maybe 5. By the end it was 15-ish, right? Something like that. Yeah.
Thank you.
I'm just wondering, after years of this and all of this integration into Facebook, has it generated interest from other teams at Facebook to start looking at Erlang and related technologies? Or have the Erlang people decided to write some C++?
We're working on it. Okay? Not really.
All right, any more questions? Oh.
I guess just this all started because you wanted Facebook's like deployment ability and logging and all of that. Like, was it worth it? Did all the years of work get you the value that you needed out of their infrastructure?
As we will grow, it will definitely be worth it. Even now, we see the value, yes.
Okay.
All right. We good? All right, thank you very much. Oh, there was one.
I would just like to know to which extent did the Facebook side or their teams actually like cooperate and help you in the process?
Because we were moving to Facebook databases, some of the things there that we noticed had to be changed inside databases themselves, and I worked directly with the teams that support those to make them happen. They were really good at collaboration with us.
Going once, going twice. I think we're good.
Awesome.
All right, thank you.
Thank you.